In this lecture, you will learn about global positioning systems, so-called GPS systems, that sometimes are used in automotive safety applications. The GPS is typically not to provide very accurate positioning, but can be used as input to other components, that in turn provide more accurate local positioning. Such components include local mapping and positioning using LiDAR, radar, and vision systems. GPS is short for Global Positioning System. The term GPS is often used as a general term for satellite-based positioning, but GPS is actually a particular US-based system. I will, however, use the term GPS as a general term of satellite-based positioning. A basic automotive GPS works by triangulating the position of the vehicle-mounted GPS through measuring the time it takes for radio signals from the set of satellites in orbit around the Earth to reach the vehicle-mounted GPS. What makes this possible is knowing the exact position of the satellites, and the satellites being equipped with very accurate atomic clocks, information that the Earth-bound receiver can use to calculate its position. As you see, only satellites that are in line of sight of the GPS receiver can be used in the positioning. There are, however, several sources of errors that affect the measurements. You will learn about these shortly, but I will first give a brief introduction to enhanced GPS systems, the differential GPS. Actually, differential GPS can remove or attenuate a majority of the GPS errors, with some notable exceptions. Differential GPS works by providing the GPS receiver with error correction information. This information is collected by having one or several so-called reference stations. These are static installations of a GPS receiver with an absolute position known with high accuracy and precision. By comparing the known absolute position with the current measurement, error correction information can be sent to the mobile unit, and then remove the errors. Now to the errors. Satellite clock errors can induce errors, but the errors are typically below 1 meter. The propagation of the signal from the satellite are further affected by the ionosphere and the troposphere surrounding the Earth. The ionospheric error is typically less than 1 meter nighttime, but can be 5 to 15 meters daytime. That is, the error depends on the sun affecting the ionosphere. Tropospheric errors can be 2.5 meters with satellites in zenith in relation to the GPS receiver, but 5 to 15 meters in low satellite elevation angles. The final error type I will introduce is the multipath problem, or the multipath error. Actually, the main type of error that even differential GPS cannot handle is the multipath error. As you can see here, a GPS receiver cannot know if the radio signal received from a satellite comes directly from the satellite or it has bounced from a building or the ground before arriving. This means that the GPS receiver overestimates the distance to one or more satellites, and potentially, depending on the other satellites' information, generate position errors. Techniques to improve the classification of signals as being reflections are available and are still being improved. GPS dilution of precision is a metric of how the satellites align for good position estimates. Here is an example. The GPS receiver only knows the distance to each individual satellite. That is, given that the red and blue dots are satellites, the receiver only knows that it should be somewhere on the red and blue circles. By knowing the position of the satellites and having a range measurement, it is possible to estimate the position. However, there will always be some measurement error. In figure B, the receiver then knows it is somewhere within the green area. Imagine now that the satellites have a completely different configuration, as in C. The green area is much larger in C than in B, and thus the dilution of precision is much higher in C than it is in B. Here's another conceptual visualization of satellite configurations that horizontal dilution of precision provide a metric of. On the left, a tight clustering of satellites, while on the right, a more spread configuration. High dilution of precision on the left and low on the right. The GPS system originated in the maritime domain. Therefore, the standard protocol used for communicating with GPS units are from that domain. When communicating with the standard GPS, the National Maritime Electronic Association (NMAEA) communication standard is typically used. It's a plain text ASCII messaging language that starts with a $sign and ends with a control line feed. It has a maximum length of 80 characters and data items are separated by commas. Here's an example of an NMEA message and its parsing. GGA is the name of the message type, in this case the position fix. The time the position is taken is provided, together with the longitude and latitude in degrees and minutes north and east. The quality of the fix is either 0 or 1. The number of satellites is an indication of the quality of the data, but even more so, their horizontal dilution of precision provide an quality indication, as you know from earlier in the lecture. The altitude is typically not as good as the longitude and latitude position estimates, with the rule of thumb of being 3 times worse than the longitude and latitude errors. The height of the geoid is a piece of information most users don't need, and I will not describe it further. However, the time since the last differential GPS update may be important for your quality estimates. If you do not have a GPS update for some time, or at all, the quality of the position estimate is rapidly decreasing. The ID of the GPS station is stated here, also nothing that most users use. The checksum just makes sure that the data provided is correct with reasonable certainty. Due to the errors and corresponding inaccuracies of GPS positioning, GPSs aren't used as the only source of absolute positioning in automated vehicles or safety systems. However, the GPS can often produce reasonably accurate information on global positioning, providing a starting point for using digital maps together with extra vehicle sensors, such as LiDARs and radars and vision systems, which can be used to generate position accurate enough for automated vehicles and safety applications. I hope you enjoyed this lecture. Today's GPS units are very small. An example of a GPS unit is here shown in comparison to matches. Finally, I have only mentioned the US GPS system. GLONASS is a Russian equivalent that many GPSs can use together with the US GPS run system. There are also other GPS systems available, including Galileo, a European GPS system, and BeiDou, a Chinese version of GPS.